Our topic today is motion. We'll be considering the cause of motion, types of motion, terms used in describing motion, and of course, the equations of linear motion and velocity time graph. At the end of the day, we'll be taking some key examples on these areas I've mentioned, and exercises will be given for you to test your understanding of the topic so far treated. Motion is said to take place when a resultant force acts on a body. Motion could be linear, circular, oscillatory, random, etc. Terms used in describing motion. The terms used in describing motion includes displacement, speed, velocity, acceleration, uniform velocity, retardation, and others. Speed is the distance covered per unit time. It is also equal to the slope of a distance time graph. Velocity is the displacement of a body per second. It is also equal to the slope of a displacement time graph. Uniform or constant velocity is when the velocity of a moving body remains constant at different times. Graphically, the graph is as shown below. Acceleration is the time rate of increase or change in velocity. In formula terms, acceleration equal to final velocity minus initial velocity divided by the time taken. Small a is for acceleration, v is for final velocity, u, initial velocity, then t is for time. Also, acceleration is equal in value to the slope of velocity time graph. Such a graph is illustrated below. Acceleration equals to change in velocity divided by change in time, represented by dv divided by dt, which is the slope. Acceleration could be uniform or non-uniform. Uniform acceleration is when the velocity of the moving body increases in equal amounts at equal time intervals. Retardation or deceleration is the time rate of decrease in velocity. Uniform retardation occurs when the velocity of a moving body decreases in equal amount at equal time intervals. It is represented as shown below. Equations of linear motion. The equations of linear motion are v equal to u plus at, s equal to u plus v over 2, all multiplied by time t, s equal to ut plus half at squared, v equal to v squared plus 2as, where u is equal to the initial velocity or speed, v is the final velocity or final speed, small letter t is for time, a is for acceleration, s is equal to distance covered. These equations are used in solving problems associated with linear motion. Velocity time graph. This is a graph of velocity against time. It is used in analyzing linear motion. This graph could be used to determine acceleration, retardation, distance traveled by a moving body, and the average speed. The information we've gathered so far could be applied in the following examples. Example 1. If a car starts from rest and moves with uniform acceleration of 10 meters per second square for 10 seconds, what distance does it cover in the last 1 second of its motion? The options are A. 95 meters, B. 100 meters, C. 500 meters, and D. 750 meters. Solution. First of all, we take the data provided in the question. The data, we are told that the car started from rest, meaning that initial velocity is 0. We are told that it moves with uniform acceleration. Acceleration A is 10 meters per second square. We also have the time taken, T, as 10 seconds. We are asked to calculate the distance covered. Distance is S. Distance covered in the last 1 second. The distance we are looking for is the distance covered when the time was 10 seconds minus the distance covered when the time was 9 seconds. S2 minus S1, where S2 equals to distance when T is 10 seconds and S1 is equal to distance when T is 9 seconds. First we take S2. S2 is obtained using ut plus half of at squared. S2 is equal to 0 times the time is 10 seconds plus half of acceleration times time squared. The time is 10 seconds. So S2 will give me 0 plus 500, which is 500 meters. Also, S1 is obtained using the same ut plus half of at squared, but this time the time is 9 seconds. S1 will give us 0 times 9 plus half of acceleration is 10, time is 9 squared. So S1 will give me 0 plus this 5 times 81. That will give us 409. 405 meters, which is 405 meters. Distance covered when the time is 9 seconds. Example 2. An aeroplane lands on a runway at a speed of 180 km per hour and is brought to a stop uniformly in 30 seconds. What distance does it cover on the runway before coming to rest? Option A, 360 meters. Option B, 540 meters. C, 750 meters. D, 957 meters. From the given question, the initial speed represented by U is 180 kilometers per hour. We are told that it's brought to rest. Final speed represented by V is 0 within a time interval T of 30 seconds. We are asked to find the distance covered. Distance represented by S question sign. First, we have to convert the initial speed from kilometer per hour to meter per second. 180 kilometer per hour is the same thing as 180 times 1000 meters divided by 3,600 seconds. This we cancel out this. 18 will give us 2 here, 2 here 1, 2 here 5. This will give us 50 meters per second as our initial speed. Using the equation of motion that contains the alphabets U, V, T, and S, I have S is equal to U plus V over 2 multiplied by time. If I fix the values, the distance covered becomes initially 50, that's the initial speed, 50 meters per second. Final speed 0, divided by 2, time taken 30. The distance covered is 50 over 2 times 30. That distance is 750 meters. The correct option is option C. Example 3. The diagram below shows the velocity time graph of a vehicle. Its acceleration and retardation respectively are A, 8 meters per second square and 4 meters per second square. B, 4 meters per second square and 8 meters per second square. C, 4 meters per second square and 2 meters per second square. D, 2 meters per second square and 4 meters per second square. Solution. The given graph is as follows. Time in seconds, velocity in meters per second, final velocity 80, 20, time here is 50, here is 90. I'll label the graph OACD. The acceleration, small letter a, equals to slope of line OA, the line representing acceleration. So acceleration is change in velocity divided by change in time on that line. That will give us final velocity minus initial velocity over time, and that is 80 minus 0 over time taken for the acceleration, 20. The acceleration is 80 over 20, which is 4 meters per second squared. Similarly, retardation is equal to the slope of line CD. Retardation will give us change in velocity divided by change in time. Retardation will give us initial velocity minus final velocity over time taken. That value will give us 80 minus 0, time taken 40. Retardation will give us 80 over 40, which is 2.0 meters per second squared. Option C is the correct answer. Example 4. The velocity v of a particle in a time t is given by the equation v equal to 10 plus 2t squared. Find the instantaneous acceleration after 5 seconds. The options are A, 10 meters per second square, B, 15 meters per second square, C, 20 meters per second square, and D, 60 meters per second square. Solution. The equation that relates velocity to time is v equal to 10 plus 2t squared. The instantaneous acceleration is obtained by differentiating velocity with respect to time. Differentiate v with respect to time. For acceleration, the instantaneous acceleration is dv dt, which will give us 4t. Therefore, when t is equal to 5 seconds, acceleration will give us 4 times 5, which is 20 meters per second squared. Option C is therefore the correct value.